everyone. It's live.
Yay!
Yay. Oh, so I don't know if you know, but we had to cancel the weekly Space Hangout on Friday because of a medical emergency in the old Cain household.
Oh no.
Yeah, so what happened was my daughter had her vaccination, her grade 9 vaccination on Friday. And so I was, big vaccination proponent. There's no way my daughter was not getting her vaccination, and she's terrified of needles and medical procedures in general. So I really helped her kind of work through the fear, and this is what brave means. Brave means about feeling the fear but doing it anyway. And she wanted to just stay in bed and was looking for all kinds of ways to avoid the vaccination. And so I got her to agree to go, and so she goes to her school, and then I get a phone call about an hour later, and it's like, yeah, this is the health department, and we gave your daughter her vaccination, and she had an allergic response. Her throat was closing up, and so we had to give her a shot of adrenaline, and we have to take her to the hospital to observe.
She had like one of those fraction of a percent anaphylactic reaction.
Exactly. Super rare anaphylactic reaction. And it had to give her some, was it epinephrine? Yeah.
Yeah.
But they're ready for this, right? Like they knew that this is a possible response. And so they had somebody on staff with the epinephrine shot ready to give it to any kid. And it was only my daughter who had the response. So while the weekly Space Hangout was supposed to happen on Friday, I was in the hospital with Chloe, and she was fine, and checked out 2 hours later and got her a big lunch, and everything was fine. And she was feeling, even after the epinephrine wore out, she's still feeling a little constricted, but it was pretty good. So
yeah, and reactions like that are usually not the vaccine, it's the egg in the vaccine.
Right. There's some kind of additive in the vaccine, some kind of stabilizer or preservative or whatever it is. And so we're going to have to go and but the problem is that now the hospital is going to get back to us, or the nurse is going to get back to us and tell us the specific vaccination that she had. And so now from here on out, we have to go through the doctor and get the vaccination done and seek out ones that don't have whatever those ingredients are, and then see if that does the trick. So it's a terrible irony. So hey everybody, thanks for joining the Astronomy Cast today. I'm going to say hi to a bunch of you, including Ed Thompson and Nancy Graziano and James Gibbs and Mick Vogel and Michael Thompson and Nancy Graziano and Helga Berkog, Giselle Sabarin, Thomas Treneker, Guido Bibra, Career the Vegan, Ross Betts, Sev Dust Bunny, and Michael Jobin, who just said period. So just period.
Well, that's a thing.
That's a thing. Let's see. Yeah, so I apologize again to everybody, and we probably could have made it, but in the end I was sort of like, I didn't want to try and coordinate missing the Space Hangout, and I could have started the Space Hangout from my phone as we were driving back from the hospital, whatever. Anyway, it was good to just kind of hang out with her and sort of help her cope with her anxiety and such. So anyway, so if you have no idea what it is that you have stumbled into, we're going to do a live episode of Astronomy Cast, episode 395, where we're going to wrap up the Standard Model, talk a little bit about baryons, and then we're going to find out where the Standard Model falls apart, where it breaks down, where we don't know what we don't know. And so we'll take about half an hour, do that episode, and then we'll stick around for your questions about space and astronomy, or the Standard Model of physics. So if you don't know how to do that, wherever you're watching this show, says that there should be like a banner inside the video that says that we're interacting live. Click that. You'll get another version of the video, but now there'll be a place you can ask your questions. You'll see all the other questions. You can vote for the questions that you like, and you can make suggestions that I will then steal and sneak into the show. So you've been warned. Okay. Anything else?
I have to admit, this is one of those shows that requires me to have like 30 windows open, so I'm not accidentally giving false information. So I'm just making sure all the things are open.
Okay, great. What are some of the kinds of things? What are some of the kinds of research that you have in front of you right now?
Like I have a list of baryons open because they come in different varieties, and who knows what questions we're going to get, but I wanted to be able to throw out some of the cooler names that I don't normally know about. Like charmed bottom is the name of a particle. And just having that in front of me pleases me greatly. So I have the list of baryons. I never remember the names of the supersymmetric particles, so I have the list of supersymmetric particles. So it's basically lists of proper nouns because I suck with proper nouns.
Well, there's probably like 40 detected and predicted baryons. So, I mean,
there's way more than that.
More than that.
That's
okay.
the problem.
Oh, yeah. Sorry. Yeah, no, there's probably hundreds.
Yeah. And I have a dog that just came in because she apparently knew how to open my door, and I need to get rid of her because otherwise she's going to sit here scratching my chair.
That. Yeah, no, you can't have dogs figure out how to open doors.
No. Yeah. It's an old house. Come on, Noisy.
Right. So once again, go ahead. Throw in any questions you've got, and we'll get at them at the end of the show. What else? Hi to Stardude Astronomy.
What?
Dirk Jeschke. Did I say Ross Betts? If I didn't, hey, Ross Betts. Okay. Let's get cracking.
Okay.
Let me know when you have pressed the coordinate button.
I need that window. I have
that
pressed
window.
It.
Excellent.
It is recording with really horrible levels. Why do you have horrible levels? Hold on.
Because GarageBand is stupid?
I'm using Audacity for the first time. And it has sucky levels.
Oh, no. It's all just ironically turned back on me now. Okay, I'm going to stop my recording. Oh, it looks so stupid now.
Yeah. Let me open up my system settings and see what happened.
Right. So you are watching the sausage get made.
Yeah, the newest version of GarageBand was hard for Preston to open, so I decided I will go ahead and use Audacity. And Audacity is like, no, you won't.
Yeah. On the Mac.
Testing. Hello. That looks better. Okay. So I'm pressing record and
auto on Audacity?
Yeah.
Okay. I press record as well.
And my levels don't suck.
Good. Then here comes your intro. Astronomy Cast, episode 395, Baryons and Beyond the Standard Model. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. My name is Fraser Cain. I'm the publisher of Universe Today. With me is Dr. Pamela Gay, a professor at Southern Illinois University, Edwardsville, and the director of CosmoQuest. Hey, Pamela, how you doing?
I'm doing well. How are you doing, Fraser?
Great. I've got nothing, no announcements, nothing to tell people or ask people. Do you have anything?
I would remind people, especially since it is Cyber Monday, if you're watching live, to go to astrogear.spreadshirt.com and check out our cool shirts, hoodies, mugs, all of these random things that you can use to inflict science-y things upon people. My favorite is our Ceres, the Other Former Planet shirt, because I'm Team Ceres.
And you have worn that many times, even on the show.
I have. We also have a Pluto shirt. Explore. Classic Pluto.
Classic Pluto. Not that newfangled Pluto.
Well, it's Pluto Planet Classic. Sort of like Coke Classic. Just right. Pluto Planet Classic.
All right. Show now?
Sure.
In the last few episodes, we've been talking about the standard model of physics, explaining what everything is made up of. But the reality is, we probably don't know a fraction of how everything is put together. This week, we're going to talk about baryons, the particles made up of quarks, famous ones are the proton and the neutron, but that's just the tip of the baryonic iceberg. And we're going to talk about where the standard model ends and what's next in particle physics. So we kind of glossed over baryons, and I think we realized we moved straight to leptons and quarks, but in fact, we didn't spend a lot of time in baryons. And I think originally, in my very small understanding, we had protons and we had neutrons. Those are your baryons. But apparently, now looking at the list, there's a lot.
There are a lot. And just to review things for those trying to follow along at home, because this is a crazy alphabet soup. And I love your phrase, just the tip of the baryonic iceberg. So we have leptons, which are fundamental particles that cannot be broken up any further. And these are our electron, muon, and tau particles and their partner neutrinos, the electron neutrino, the tau neutrino, and the muon neutrino. Then we have the quarks, also fundamental particles, up, down, charm, strange, top, bottom. And these combined are called fermions, and fermions are things that have a multiple of spin 1/2. So they have a spin of a half, 3 halves, 5 halves, spin half is the key. And because of that, they follow the Pauli exclusion principle, and you can't have two things with the same spin in the same energy level. So for instance, in an atom, you will have a spin up and a spin down sharing an energy level. Okay, so that's the fermions. Then we have the bosons. These are the things that carry force, give us mass. So we have the photon, which is tied to the electromagnetic force. We have the W minus, the W plus, and the Z boson, also called the Z0 boson. And these are what handle the weak force.
Whew.
We also have
nice
the gluon.
The gluon, okay, keep going.
Gluon, which is the strong force, and the Higgs boson, which gives us mass. Okay, so those are all the fundamental particles. Everything else is a non-fundamental particle. So everything else has to get built out of these fundamental particles.
And one of the things that gets built is the baryon.
Exactly. So things that are made of quarks are called hadrons. And hadrons are generally grouped into how many quarks make up the thing in the hadron. So we have mesons, which are combinations of two quarks. We don't deal with those in real life generally. And then we have the baryons. Baryons are what we deal with all the time. You and I are pretty much baryonic matter.
Right. We are made of baryons.
We are made of baryons. This is an awesome thing. We are fermions and we are baryons. And those baryons that make up us are made out of 3 quarks. In fact, they are made up of the ever so boring up and down quark. And these are what are called the protons and the neutrons.
And so what is the sort of the major difference between the proton and the neutron? I mean, we know that it's neutrons have a neutral charge while protons have a positive charge. Are there any other differences? So
the proton is an up, up, down. The neutron is an up, down, down. And yeah, they're basically very close to the exact same mass. The biggest difference is, as far as we know, protons are annoyingly stable. Now, I say annoyingly stable because a lot of theoretical physics would like these suckers to decay. It just makes the physics actually work. But as near as we can tell, they are utterly rock solid, not changing their identity, stable. The neutrons, on the other hand, when they're not bound up inside of a nucleus of an atom, they like to decay rather quickly in about 100 seconds or so.
What do they decay into?
They actually decay into a proton, a electron, and a electron neutrino.
Oh, okay. And I guess that's, when we talk about neutron stars, which are this degenerate matter, right? This is where you've taken you've artificially taken all the protons and all the electrons and you've mashed them together into neutrons, right? And I guess it's just the opposite way.
And this is where you end up with protons and neutrons being close to the same mass, but not the exact same mass. So that difference in mass is how you get both a proton and an electron out when you let the neutron sitting on your shelf decay.
Right, right. And as you said, they do adhere to the Pauli exclusion principle, right? So you can't put two protons, neutrons, etc.
No. They don't. It's the electrons that are spin half,
right,
and our Pauli exclusion principle. The way these work, because quarks, they're also spin half, but they combine, and it just works out that you end up with spin 0 if I'm reading the chart I'm looking at correctly. Anyways, they don't obey the Pauli exclusion principle. They're good.
Now, we've got a lot of building blocks. We've got all, the 6 different kinds of quarks that we know about, and yet the 2 major kinds of baryonic matter in the universe, right? With the proton with the up, up, down, and with the neutron with the up, down, down. But with all those other combinations, there must be a lot of other baryonic matter out there. So what else is out there?
Well, they go on forever, it feels like. So if you think about it, we have these 6 different quarks, and then we're looking to combine them in combinations of 3. And so that is one heck of a recombinatorics problem. And what's kind of awesome and disturbing at the same time is people have gone through and named pretty much all of the combinations. And this means that we end up with really funky names. So if you combine a down quark, a charm quark, and a bottom quark, because you can, you end up with what they call a charmed bottom.
Right.
And that's
do we have to put explicit language on this episode now?
Oh, anyway. That's its actual scientific name.
Yeah.
We also have the double charmed omega particle, which is a strange charm. It's just sort of like at a certain point, they just decide to start amusing themselves while naming these things. But the thing is, all of these things decay, and some of them actually haven't even been observed. So, for instance, we've named the charmed bottom, but it's never been observed. We don't know what its decay route is. We don't know if it does exist, how long it exists for. But that's what we're looking at.
Right. Now, like how many different ways can you take strange, charm, down, up, down, charm, right? You just keep putting those combinations together and you're going to come up with new particles. And you can work out the math, I guess. You can work out what the spin is going to need to be, what the charge is going to be, but it's not, you don't know whether this can even exist.
Exactly. And what's cool, though, is we can work out so much about it. So, for instance, we refer to baryons in general as falling into 2 different families. There's the angular momentum half baryons. This gets into crazy quantum mechanics stuff that you really need 2 years of quantum mechanics to understand. I'm not going to torture you that much. Suffice to say, angular momentum half and angular momentum 3/2 baryons. And all of the 3/2 ones, all of them are unstable. So we have these 2 different families of particles, but we've detected things in both families. So for instance, a delta particle, which is made up of 3 different ups, because why not combine 3 things going up? That sounds kind of positive on a Monday afternoon. We know it has a rest mass of 1232 mega electron volts. We know it decays into a proton and a pion, and we know how long it lasts, which is way less than a second. But what's cool is we have, by slamming things together in particle accelerators to generate vast amounts of energy in a very small place. We've been able to create circumstances that allow that energy to rain out into all of these different unstable particles that we can then study. So we have the ability on the math side to go through and say, okay, we've got 6 different things that we can combine together in all of these crazy different awesome ways. There's a triple charmed omega particle, for instance. That is a kind of awesome idea. There's also a charmed double bottom omega particle, just if you want to get weird.
But with all of these combinations, though, right?
Mm-hmm.
Like these don't occur naturally in the universe.
So there's a difference between something not occurring naturally and not being stable. All of these things probably exist in the universe for fractions of a second. When I say fraction, in a supernova, in a collision between 2 cosmic rays. So you can imagine a situation where you have a high energy event that isn't a supernova. So perhaps a coronal mass ejection lets off a cosmic ray and it's zipping its way through the universe, and it just happens to collide with another particle zipping its way through the universe. And they combine for that fraction of a moment for 10 to the minus 23rd, 24th of a second, create a sigma particle, a charmed sigma particle, whatever it might be that falls out of that energy.
Right. And with way more energy than the Large Hadron Collider could ever produce.
And that's the wild thing, is we're working to catch up with the universe. The universe just does this because it has really big naturally occurring magnetic fields. We have to do really bad things to the power grid to create these really big magnetic fields.
And so this is one of the great things about the Large Hadron Collider. Everyone's afraid that the LHC is going to destroy the planet, but the reality is that it generates energies that are vastly, at many orders of magnitude, less than the universe does all the time.
Exactly.
So we talk about, okay, so maybe these particles are being generated. In fact, vast amounts of them and they are all decaying. And so the trick is that nothing else is stable in the way that protons and, neutrons arguably are.
Yes. And so this is where we live in a reality where, yeah, we occasionally do experience muons in detectors because they rain out of the upper atmosphere. But most of our day-to-day interactions are protons, neutrons, electrons, and that's about it. Up and down. That's all we've got. Up and down quarks.
Right. Okay. So sort of the second part of this show is we want to talk a bit about where are the gaps, where are the holes, and what comes next. So let's do this in 2 ways. One is, what are some things that we know about that we don't know how they fit into the model?
The biggest one, which is kind of ridiculous to admit to, the biggest one is actually gravity. We talk about there being a graviton boson, maybe, sort of, we don't know. But as near as anyone can calculate, gravity just doesn't fit in at the quantum mechanics level. So there's that big problem.
Mm-hmm.
Looking beyond that big problem, we don't know how to explain dark matter and dark energy. And the one thing we do know about dark matter is it's some sort of non-baryonic particle. So it's something that must be stable, or at least is constantly regenerating, that doesn't interact via the electromagnetic force in a way that we know how to deal with.
So could one possibility be then that maybe there is some other stable form of some other stable baryon that was maybe generated during the Big Bang, or is still being generated by all of these cosmic rays, bumping into each other, and this is somehow producing some particle that at a higher level of energy than we can create in the lab that has these properties?
Well, the issue seems to be that quarks are quite happy to interact via the electromagnetic force. So since we know that dark matter is not interacting via the electromagnetic force, this is where it doesn't deal with light as light passes through the universe, except to bend it. It doesn't interact in any of the normal ways that other stuff does. That means that since baryons are made up of quarks and they interact via the electromagnetic force, we're looking for something that isn't a baryon. And so we're looking for something outside of all of these awesomely named quark-made particles.
So right now, then, where do particle physicists think dark matter exists on, compared to the standard model? Like, which group would it probably be in?
It's not. That's the thing.
No group.
It's
not
outside.
a lepton. It's not a hadron.
It's
not
outside.
It's outside.
Yeah, it's a non-baryonic particle.
But is the thought okay? So then, what? I mean, I understand that it's outside, but particle physicists have done plenty of math and done plenty of predictions about what dark matter particles could be, and they're going to try and create them, and with things like the LHC. So, what kind of characteristics are they looking for? I mean, give us something.
So we're currently at a stage where it's hard to say that folks are doing much more than looking at the universe, putting constraints based on what we're observing, on what we expect to find, and kind of hoping that things that fall out of theories like supersymmetry, which we'll get to, explain what we're observing. So we know that there is a very small cross-sectional radius for collisions between dark matter particles. We see this from looking at how clouds of dark matter pass through one another when superclusters interact. We know that it doesn't interact with the electromagnetic force. We know it does interact with gravity. That's kind of where we're at, and different people are going down different rabbit holes trying to find a rabbit to pull out and call dark matter. So we have some folks that are going down loopy gravity, some people that are going down string theory, some people that are going down supersymmetry, and string theory actually can go down wherever it wants and call itself supersymmetry, or call itself string theory rather.
Right.
So we don't know. We have a word, non-baryonic dark matter, and that's a good word. And that's as firm as our observational understanding really lets us stand right now.
So if you were able to generate it in the Large Hadron Collider, how would you know that you found it? How would you know that those are the characteristics of dark matter?
Well, what we're looking for as we crank up the Large Hadron Collider and prepare to crank up the cyclotron at Fermilab, what we're looking for are significantly more massive particles than we've found so far, and different kinds of things in supersymmetry are starting to get predicted that have these higher masses and don't interact, maybe. But I mean, honestly, we're sort of grasping at straws saying we need a weakly interacting massive particle. Let's see if we can get a massive particle that weakly interacts to fall out of the collisions.
Okay, so that's one, which is dark matter. And now dark energy, I guess, is another one. Maybe particles appearing, but maybe it's just space itself, right?
Right. So dark energy has no explanation. We don't know where the explanation is going to fall out of. What we do know is attempts to explain dark energy using vacuum energy, which is that flux of particles coming in and out of reality because there's just this background energy that they can use to temporarily exist. When we start looking for leftover energy from things popping in and out of existence, all attempts to use that leftover to explain dark energy is off by like 120 orders of magnitude. So that's just wrong.
Mhm.
And then there's other things that leave us perplexed. Like standard model physics doesn't require the neutrino to have mass. And the problem is, we know from a variety of different experiments that neutrinos that are formed with one identity, formed as an electron neutrino, for instance, can transmute into a different type of neutrino, like a tau neutrino or a muon neutrino. And this ability to flip identities requires the neutrino to have mass that can go into that identity flip. So that's not explained. And then there's just the whole fact that why do we have so much matter and so little antimatter in the universe? That doesn't fall naturally out of anything.
Okay. And you've made a couple of references now to supersymmetry. So we actually did an episode on supersymmetry quite a few hundred episodes ago. But can you give sort of us the short version of what supersymmetry is?
So the short version is that there is a entire mirror set of generations of particles. So we talk about the particles that we normally deal with falling into three generations: the generation that corresponds to the electron proton up and down, and so on through, going from the lightest and most stable to the heaviest.
Right. I remember that. That was a couple of episodes ago. We talked about those three generations.
So
right?
Take those exact same three generations, flip them over, and call them the supersymmetric particles. And so these are essentially super partner particles. So we have for the photon, we have the photino. For the gluon, the gluino. For the leptons, we have the sleptons. For the neutrinos, we have the S neutrinos. I don't know how you say
you put
S
an S in front of everything.
Exactly.
Right. I know. For like instead of like the top quark, you get the stop quark.
Yeah. And so the idea is that all of these partner protons and neutrons and or I guess photons and bosons, all of these partner things, they're there to basically balance everything out, and they have different masses, and these different masses start to crop up as explaining what dark matter is and helping to allow to fix the problems with vacuum energy. Maybe, we don't know, and that's where it all gets highly, highly confusing.
And so, if true, these particles are going to have incredibly high masses compared to the regular masses of the partner particles, right? So
exactly.
And so there's so much, there are limits to what even the most powerful collider possible, the Large Hadron Collider so far, on what kinds of particles it can actually generate. And so these particles might just be beyond what it can create.
Exactly. And it's hoped that the top quark's sister particle, the
stop quarks, yeah,
is actually the lowest mass of these and is something that's potentially within reach. So we're trying to find that. So we're not sure.
If I understand, the recently upgraded Large Hadron Collider can just reach the stop quark.
And that's the hope.
Yeah.
So we're looking. We're looking. And it's tricky. So they do have differences. So for instance, the S fermion, they're spin zero particles. So they're going to behave without that Pauli exclusion principle. They're just going to act differently. And we're hoping that the way they act differently allows them to explain dark matter. And we're hoping that the predicted energies, at least for the stop quark, is in reality as low as it's theorized to be and is thus observable. Now, if it's not, that doesn't mean that anything's wrong with the universe. It just means we get to keep looking, and particle physicists still have a job, and there's no Nobel Prize on the imminent future, but hey, maybe there's funding for bigger and bigger accelerators.
Does supersymmetry, I mean, one of its things is that it will help unify gravity into the standard model, right?
It tries to. I wouldn't say it succeeds, but it works towards that. We actually don't have any theories that are fully successful at unifying quantum mechanics and relativity.
Wow.
Yeah.
It's kind of amazing. I mean, it's pretty, I mean, you think about the future people and they'll be able to look back, hopefully, if this ever gets figured out, right? And they'll be like, look at those people that back then they didn't know that here's how you unify gravity and the standard model.
But that's really an internal prejudice. It's the human desire for there to be one underlying cause that explains everything. One of the things that people find extremely dissatisfying about the standard model is I think it has 19 finely tuned constants in order to work. And people don't want a universe that's filled with constants. They don't want a fine-tuned universe. They want a plop down these laws of physics and it just goes.
Right.
And it could be. Gravity doesn't unify.
There's a great game. There's a game coming out that I want to get called No Man's Sky. I don't know if you heard about this.
Yeah.
But in the game, the whole universe is procedurally generated. And so no matter where you go, every part of the universe has been figured out sort of just in advance by the math. And it's the same thing. They pick these very specific, they picked a seed that then produce everything. And if they pick a different seed in their math, that it creates something different. And this is sort of this idea that, that our universe exists the way that it does just because all of these variables ended up the way they are, all these constants, right? And that if they'd end up a different way, then gravity wouldn't work properly. And, and so you could have all kinds of malformed universes from our perspective, but this is the one that was just barely suitable for life.
And that gets back to the ideas of multiverses, which I think we did an episode on. And so there's really nothing wrong with gravity not unifying. It's just uncomfortable. And sometimes we just need to be a little bit uncomfortable.
I need my whole universe to fit on a t-shirt. It's gotta happen. Very small font is fine, but I still need to have the theory of everything on my t-shirt. Okay, cool. Well, thanks a lot, Pamela. We're gonna go in a different direction next week.
We really are. Next week, we're going to talk about happy books and all of the nerd stuff that you can get in this season of giving.
We will recommend our favorite things to get people for the holidays.
Whatever holiday,
whatever holiday you celebrate. Yeah, exactly.
Birthdays. My birthday is in December.
That's right. Okay, cool. Well, thanks again, Pamela.
Sounds great. Okay.
So you need to export it as well.
Yep.
So
I do know how to use Audacity. It just didn't.
I didn't know. You don't have to yell. Okay. Export. And then we will talk about other things.
Yes.
No, we're not. We're going to talk about the same thing, I'm sure. Oh, my Dropbox is full.
I'll clean when we're not both on, though.
Okay. Well, I won't upload until you've cleaned it. And remember, we have to stick around and do an advertisement at the end of this.
Yep.
Okay. I'm going to look at some questions. Nancy says, very relieved your daughter is doing better. Nothing scares a patient more than having a medical emergency, even a minor one. I'm not sure I would have been so nonchalant about it. It's funny. I was so certain there was nothing wrong that I wasn't even that panicked about it. I'm like, oh, okay. All right. Let's see. how can there be a gravitron if Einstein explains gravity as the slope or bending of space-time? Surely if Einstein was right, there would be no need for a graviton.
And that's the problem.
Right, but isn't it like the question that you want to ask is, how does gravity get communicated? Right? So we know it's the bending of space-time, but how does the object know how bent space-time is? And that's, in theory, that's what the graviton exists for, is to literally
the graviton could essentially remove that whole space is bent concept and make that just into a paradigm of how you try to understand the universe. Whereas Einstein says, no, the universe is actually bent.
Right. Okay. But it's like, how does, I don't know. I mean, when you look at all the different particles and look at all of the bosons that we talked about, right, that you could have that same question. How does, I don't know, how do two atoms know that they should be stuck together with an atomic bond?
They know because there's
the gluon
particle communicating that force. Whereas with gravity, its universe is bent and everything is responding to that change in the geometry of space-time.
So if the graviton is true, then Einstein is wrong.
No. It isn't that he's wrong. It's that his paradigm was incomplete.
Right. In the same way that Newton's theories fall apart at the most at the places where relativity takes over. In theory, if a graviton is discovered, then that will give a better understanding of the way the universe works than even relativity does.
Right.
To all intents and purposes, relativity explains the universe with incredible precision, and the graviton has to do that and more. So step up, gravitron. Let's see.
There's no second R. Graviton.
Graviton, not the Gravitron. Gravitron, I believe, is a ride at the amusement park where you get stuck to the side of it. Fred Miller says, the innermost parts of the Hercules A jets are not visible because of the extreme velocity of the material, which causes relativistic effects that beam the light away from us. Are they talking about effects other than gravity?
No.
Well, they're talking about magnetic, the magnetic forces that turn the particles into these jets that are coming out of the supermassive black hole.
Well, it's more complicated than that. So, I'm not seeing the comment. How far down is it?
I don't know. Right now, it's the one that says currently answering. It's by Fred Miller. So,
okay, but
So the question is...
So read it again.
So it looks like he's referencing some new piece of astronomy research. So the innermost parts of the Hercules A jets, Hercules A, I believe, is a galaxy, and so these are the jets coming out of a supermassive black hole, are not visible because of the extreme velocity of the material, which causes relativistic effects that beam the light away from us. Are they talking about effects other than gravity? Where is this?
So Herc A is an active galaxy. I'm trying to figure out if it's a BLAC object, because that's slightly different physics.
Oh, here we go. He's got a space telescope press release that we'll take a look at.
What's the link?
It's I'll put it in the chat if you want.
Yep.
So it's a multi-wavelength view of radio galaxy Hercules A. It's got these two crazy jets coming out of it.
Crazy jets are a kind of normal thing.
And the innermost parts of the jet are not visible because of the extreme velocity of the material, which causes relativistic effects that beam the light away from us. So, in other words, at the close to the galaxy, the jets are moving so quickly that the light is, when they say beam the light away from us,
So
is Is that a
Okay, I'm
bad?
pretty sure this is badly written is what we're dealing with. So we're dealing with a couple of different things. As it's moving away from us, its color is getting changed. So its color is preventing um, could be preventing it from being visible because it's shifted into a different wavelength. Or as it's getting beamed away from us, it could be getting obscured or something like that. But the idea of it getting beamed in a different direction, that doesn't make the light go away. Now, it could be like a laser beam that because it's tightly focused and going in a different direction, the light just isn't reaching us. But that this is poorly worded. I'm not sure what they're trying to say, and now I'm going to go find someone to ask. But it's either that we're not seeing it because the light is literally shining in a different direction and hasn't reflected off of something in order to be seen, or what they mean is it's the particles that are giving off the light have been accelerated to the point that the light is coming off in a non-visible color. I don't know what they mean. It's poorly worded.
Yeah, it says that they're radio visible, but they're not. But then later on, the jets become visible in the regular spectrum, but close, they're only visible in the radio.
Okay, so they're just referring to everything is redshifted to the point that it disappears out of other wavelengths and lands itself in radio.
Crazy.
It's not crazy. It's normal. It's just geometry.
Ed Thompson says, Graviton's just bent my brain. Join the club. Ross Betts says, could a supermassive black hole act as an extreme particle accelerator? And how? In fact, isn't this, there's this mystery of these tera electron volt cosmic rays that were striking the Earth's atmosphere, and then these are the ones that we're detecting with these with the what's the name? It's your favorite instruments.
There's the
salt,
like Whipple Observatory and stuff. Yeah,
the
Shrinkov detectors.
Yeah, the Shrinkov detectors, right? And
salt is optical.
Yeah, and they didn't know where these things were coming from. Like they didn't think there was any way that particles could get that much energy.
And the Herc-A example that we just pulled up the link for, that's a supermassive black hole that is producing hyperaccelerated particles through its jets. It's supermassive black holes that are in the process of feeding. They have this high velocity disk that as the charged particles rotate, they generate a magnetic field. And it's because the stuff orbiting near the supermassive black hole has to orbit so quickly. If it's charged particles, it makes a huge magnetic field, and it's the magnetic field that's doing all of the accelerating.
But it definitely acts as an extreme particle accelerator. And this is the thing, right? These cosmic rays strike the Earth's atmosphere, moving close to the speed of light. Each one has billions. Is that right? Am I getting it right? Tera electron volt? Billions of times the regular electron mass, thanks to all the energy. And the Large Hadron Collider only wishes. And astronomers had no idea where these were coming from until they figured out supermassive black holes actively feeding and generating these relativistic jets. So it's an amazing story.
And what's amazing is we've only figured this out in the past 20 years.
Yeah. And I always think this is classic. Like you go back and watch Cosmos, and in the first episode of Cosmos, Carl Sagan says, like this is 1980, right? He says, and there's quasars, and we don't know what quasars are. Maybe,
and now we have a unified model.
And now we have a unified theory of them, right? Although he kind of, maybe they're, I forget what he says exactly, but you watch that and you just want to scream at the screen. It's supermassive black holes. We know now.
I do miss the day of hand-drawn little monsters sitting in the centers of black hole, sitting in the centers of galaxies. Because I think every galaxy astronomer who worked on active galaxies and quasars had that one hand-drawn monster, and they were very pleasing.
Michael Jobin asks, can dark matter and dark energy combine to make baryonic matter?
No.
Okay. And And Mike Vogel asks, if our supermassive black hole would start feeding actively, how much material should its accretion disk have to be visible from Earth with the naked eye? A few solar mass objects or a huge amount? I know the answer to this.
Go for it.
Never. So the one, because of the incredible distance that the supermassive black hole is, you would it would, even if it was generating, it was actively feeding, it would be producing very little. It would not be very bright compared to a bright star that's nearby. And someone did the math. But the other part is that the dust of the center of the galaxy would completely obscure it. So you literally, we couldn't, no amount could go into the supermassive black hole to be visible from the Earth. In optical, yeah.
Right. Yeah. If it ate like a cow, we could see it in X-ray.
To be visible from Earth with the naked eye. So the point is that no amount would ever make it visible with the naked eye.
Because of obscuring dust. Because
of the obscuring dust. And even if there was no dust obscuring it, it wouldn't get much brighter, right? Like you would think like, oh, we're in the galaxy.
Something's wrong with the physics there, because the amount of light given off by the accretion disk of a feeding quasar is greater than the sum total of the rest of the light in the galaxy.
But it's also the distance that we are away from it. So we're, I forget, 100 and what are we? We're 30,000 light years to the center of the galaxy. So someone did the math and showed that it would be not much brighter than a star. I can dig up that if you want at some point.
It sounds like there's probably some math errors in it.
Okay. Let's see. Zach Cody asks, should we go to Europa or Enceladus first? Which one's more likely to have life?
Europa. Which makes a case for going to Enceladus first and figuring out what we're doing.
Okay, so Europa probably is more likely to have life. Which one is easier to detect the life if it is there?
Probably Europa, but again, we want to figure out what we're doing first. So going to the place less likely to have life to figure out our technology before we kill everything probably makes the most sense.
I would say Enceladus, because Enceladus is actively spewing the water out into space. So you could fly through the plume, taste it, and see if there's any organic molecules in there.
But that wouldn't necessarily be enough to definitively prove whether or not there's life. You need to actually go down, because if all of the life is clinging to deep sea vents, you couldn't get conclusive evidence without going down to those vents.
Yeah, but I'm just, like with Europa, potentially it's 100 kilometers down. So there's like no way to get at the life on Europa. But with Enceladus, it's theoretically potentially spewing stuff out into space. So maybe there's a chance, super off chance. That's all.
But if you think about it, like geysers on Earth aren't where you go in order to collect bacteria samples generally.
But if you sampled the water from a geyser on Earth, you would find bacteria in it, wouldn't you?
Maybe, but not necessarily. And that's the problem, is what we collect that is getting forcibly pressed through crevices in the surface isn't going to be a representative sample. It's going to be a surface sample.
Yeah.
And if all of the life is clinging down deep, you have to go down deep.
Yeah, no, absolutely. And as soon as that method of digging through 100 kilometers of ice is available, we should totally do that.
And I'm just saying, let's practice that at Enceladus first.
Although there may be geysers on Europa as well. And if so, then the method will work on both. Bevo LJ says, do these exist in auroras? So I guess we're talking about,
I need more words.
Some of the, I'm guessing we're talking about some of the, like, we're talking about the particle accelerators, particle collisions. Are there large hadron style particle cascades happening in auroras?
They're a bit lower energy. So there are still significant fractions of the speed of light particles hitting our atmosphere when we see auroras. And what we see is often part of that cascade of particles. But these aren't the super high energy particles that we end up talking about when we're talking about muons forming. Those are, for instance, gamma rays versus what we see when you see the oxygen light being given off that is some of those beautiful colors in Aurora.
Oh, he clarified and says, was speaking of baryons. So are there baryons in auroras?
Yeah. Auroras are totally baryonic.
Right. They are charged ions, and ions
are by definition charged.
Yes, they are ions, and ions are just protons.
It's like oxygen and nitrogen and stuff like that in our upper atmosphere that's getting hit often by charged moving electrons.
And Bevo, we need to do that. We're going to do a collaboration. We're going to play some Kerbal Space Program live and do that. So ping me on Skype and we'll make that happen. Ross Betts asks, is there any potential that our universe is the information horizon of a black hole? The old, are we living in a black hole question.
I don't think so.
We actually have asked you this question probably 20 times now. And your answer, as I recall, is the difference between the universe as the singularity and a black hole is that back in the singularity, it had all of space-time inside of it, and then that's been expanding. But if you take a black hole, it's embedded in space-time. It doesn't have any space-time inside of it.
Right, but I think he's actually asking a third nuance, which is there a ginormous multi-universe sized black hole out there that our universe exists on the event horizon of? And that's a question for philosophers.
Or yeah. It's funny, like if you take all the mass, I did the math at one point using Wolfram Alpha, and I took the mass of the universe and then calculated that as a black hole. What was the event horizon of a black hole with the mass of a universe? And it was the size of the universe, I think. Anyway, I was having a conversation with Coberline about this. He says it's pretty weird how low density you can get a black hole if you feed the entire universe into it. So that's weird. We're still going to do a video on that. David Joseph Wesley says, what do you guys have to say to the plasmic universe and electric universe folks? Stop bugging us?
Yeah, that's kind of, they actually like periodically mail us things.
My favorite response to this is actually the one that Brian Coberline did. If you search for Brian Coberline and electric universe, he's got a great just list of tests that concept fails on. And so they're not interested in coming up with a rational explanation for the universe. They're more sort of an us versus them kind of philosophy, which
they are part of what proves that once someone has a misconception, it's almost impossible to get rid of that misconception with data.
Yeah. I mean, the thing that's blowing my mind right now is this flat universe madness that's going around. And I've
missed this somehow.
Really?
Yeah.
Oh man, on every video I get someone popping out of the woodwork claiming that there's that the earth is flat.
Oh,
flat earth. Not flat universe, flat earth.
You say the universe is flat. I'm not sure what you're talking about.
Yeah, no, they're right. We call those PhD physicists, Nobel Prize winning, and they're right. No, flat earthers. Yeah. So the flat earthers, like somehow flat earth has taken a new life. And
oh dear.
Yeah, and the level of mental gymnastics that they have to do, like, well, that means that the moon is only. Anyway, I barely even. this point. It's
That
crazy.
no,
Yeah.
no.
So anyway, electric universe is over. Now it's the flat Earth. Everything goes in cycles. It's the age of Aquarius.
At least the flat Earth people don't mail me things.
Yet. Zach Cody asks, on the idea of the multiverse, is there anything to the impression of other universes on the cosmic microwave background?
No.
Not yet.
We're looking.
That is definitely one of the theories, that you would see, echoes from other universes on the cosmic microwave background radiation, because we see everything. Cosmic microwave background radiation is just does everything for physics. Hugo Burnham asks, what happened to all the antiprotons?
That's part of the matter-antimatter problem.
We don't know.
Yeah.
David Joseph Wesley says, I've got a friend who takes these theories so seriously and has thrown out the standard model, trying to shake him off of it. So, have him read that article from Brian Koberlein, and I wish I could throw a link at you, but I'm sure someone can throw a link into it. Search for Brian Koberlein and Electric Universe, and then he'll have the tests. And so find out from your friend if he wants to believe this because he really enjoys the idea that that it's a conspiracy theory, that there's some kind of some kind of in-group with physics, and they're not letting the outsiders participate. And right, I mean, the thing is that nature,
broken people. They're just broken people.
Well, I think people like that narrative, right? That this is the physics, and they don't like it. Look, it all makes sense, right? And I understand that. But nature doesn't care. Nature has its laws, nature has its evidence, and it's not about a conspiracy to, the great thing about experiments in science is that anybody can just do the same experiments and find the same results.
I think one of the things that is saddest is we regularly get emails from people who I'm guessing are otherwise normal, delightful people who have had that chain of thoughts that you can only have if you're not well educated in physics, and they earnestly think they've disproved various key aspects of science or have solved various key aspects of science, and they think they're going to get a Nobel Prize if only they can find someone to do the math for them.
Yeah.
And it hurts because so much education is needed in order to understand a lot of these problems. And unfortunately, that logic that your stomach does trying to make sense of our world, it doesn't work for these things.
Yeah, like let your intuition explain spooky action at a distance, right?
Right.
Or various things in quantum mechanics, or quark spin and all this kind of stuff, that that step one, like your ante into this game, is to understand the math and to be able to do the math at a level that you can recreate the math that's done in these various papers, to understand it and be able to do it. That is like, if you think that Einstein was wrong, step one, be capable of doing Einstein's math as well as any grad student, PhD person, right? Like that's step one. And if you can do that math and recreate the calculations, and then you start to see things that are flaws in that math, then that's your starting point. But you can't start with your intuitive instinct about how everything's at a cognitive resonance of the crystalline structures of the ergosphere.
Yeah, I have to say I am so grateful for MIT putting all of their physics lectures open source, because that is now kind of my please go take these courses thing that I can point people to, because university is out of the price range of pretty much everyone. This is why people go into debt to go to university. And not everyone can afford that level of debt. And because of these open courses, I hope more and more of these people that must be passionate about science, because if they weren't, why would they formulate these ideas? It's my hope that more and more of them can actually go turn this passion and misunderstanding into a true understanding.
Yeah. Yep. And that's usually the response that I have, which is, that's great. Do the math.
Yeah.
So it's
And
never
I'm
been more
not doing
accessible.
it for you.
Not going to do the math for you.
I do not do other people's math.
Yeah. Yeah. You have enough trouble with your own math. Math is hard.
I hate math.
Okay. Well, I think we've gone a few minutes over, so let's wrap things up. Thanks everyone for joining us this week. Thanks, Pamela. I think everything's back on schedule. No vaccinations on Friday, so I think we should be good.
Sounds good.
For the weekly Space Hangout on Friday. All right. Thanks, everyone.